Hello, in this lecture, we are going to discuss certain things that is required for integration. Okay, so yesterday we were doing a few questions of integration, and today we are going to take it forward by some introduction to some terms like simply connected regions, multiply connected regions, and things like that way. Okay, so yesterday we left our discussion on I think ML inequality. Okay. Now today, let us start with something called as simply connected region and multiply connected region. Now you would be wondered why I am doing this. Okay. So as you are aware that as I go further, I will need these terms quite often. Okay. So what are simply connected regions? So simply connected regions are those regions. So I would say a region R is called as a simply connected region is called as a simply connected region if every, mind you, the word is every closed curve C in R can be shrunk. Shrunk in Hindi means सिकुड़ना. Can be shrunk without going outside the region R. Without going outside the region R. Okay. And another definition that pops up is multiply connected region. Okay. So another definition is multiply connected region. So what is a multiply connected region? The region which is not simply connected, a region which is not simply connected is called as multiply connected region. Okay. Now, how to understand this? So let us make a circle. So let us first try to make a circle. So let's just try to make a circle. So here it is. I'm just trying to make a circle. Okay. So let's say I'm trying to make a circle. So I made a circle here. Okay. And in this circle, if I take any curve. So for example, if I take any curve inside this circle. Okay. So if my region R is, let's say, a circle of radius small r or anything, you take any curve. I'm not saying always enclosing origin, any curve, any closed curve. You'd find that if I try to shrink this curve, I will eventually end up being in the region R only. Eventually, I'll be in the region R only. This is my region R. This entire thing, the blue region is my region R. And if I take any sort of closed curve, I will eventually end up being in the region R only. Yes or no? But what if I take an annular region? What if I take an annular region? Let's say if I'm not doing this and if I'm doing this. Okay. So if I'm doing this. Okay. So if I'm making an annular region, annular means now you are in between the two concentric circles. Now you are in between two concentric circles. So this is your circle 1. This is your circle 2. Okay, let's see if I just make it with some different colors so that it is okay. Now understand my point. I'm talking right now about the annular region. Annular region is the blue region here. Okay, so blue region I'm talking about. Now you try to make any curve. Okay, like these curves will do. There is no issue. Eventually, if you shrink these curves, you will end up getting into the blue region. But the condition written was every closed curve C. So if I write every closed curve C, then this curve would also come into the definition. This is a closed curve. And if I try to shrink this curve, I will eventually end up getting into the red region. I mean, pink region. So clearly I'm out of the blue region. In other words, if I say my annular region is, let's say this, if I take any curve of this fashion, of this sort, and like which okay, and my annular region is this. So this is my annular region which I'm shading right now. This is my annular region given by, this is my annular region. Let's say if you just consider this as a circle. So if my, this is an annular region, and if I try to take any closed curve like in this fashion, and if I try to shrink it, eventually I will get up into a region which is not yellow. So these regions are called as multiplicative regions. So always understand, like regions like these, this is a multiply connected regions. Okay, but region like this is a simply connected region, because here I have not taken zero. Here, what is the region? It is a punctured disk of radius r. By punctured disk, what do I mean? I mean that my origin is out of question. So my origin is out of question, and I'm making a circle. So I'm making a circle, origin is out of question. So what will happen? This is the region that I'm doing. And if I take any closed curve of this fashion, if I take a closed curve in this fashion, and if I try to shrink it, eventually I'll end up getting into origin. And clearly you can see that origin is not part of this region. So this is a multiply connected region. Okay. What else can be a simply connected region? Let's say if I take this sort of region. Okay. So this region is what? This region is simply, this is a simply connected region. Yes or no? So if I just take real part of z greater than equal to 0, what does it mean? It means I'm talking of region lying to the right of the y-axis, including the y-axis. Because see, real part z equal to 0 means what? It means x should be greater than equal to 0. X greater than equal to 0 means the region that I'm shading right now, I'm talking about that. It would include, or it would include y-axis. I'm not saying that, but overall, including y-axis and towards the right of the y-axis with the region. Take any closed curve. Take any closed curve here. Any, like every closed curve, in fact, every closed curve will shrink into the region real part of z greater than 0. Mind you, when you are making closed curve, you should not go out of the region. I'm talking right now inside the region only. That is, if I have to make any closed curve, I have to make inside the region R only. I would not say, let's say this is my curve and why I'm not shrinking into the region real part of z greater than equal to 0. No, this is not the case. I'm not saying this. I'm saying take every closed curve in the region R given by real part of z greater than equal to 0 would eventually end up being in real part of z greater than equal to 0. Okay. Now, this brings me to a very important theorem in mathematics that is called as Cauchy's theorem, Cauchy's integral theorem. Now, what does Cauchy integral theorem says? So Cauchy integral theorem says that if fz is analytic, if fz is analytic and its derivative, its derivative are continuous, its derivative are continuous at each point, at each point within a, at each point within a simply connected region, within a simply connected region, let's say R, then for every closed curve C, for every closed curve C in R, integration fz dz over C comes out to be 0. It comes out to be 0. Okay. I hope this is fine. Okay. So understand my point. This was called as Cauchy's integral theorem. Okay. This was called as Cauchy's integral theorem. So how to go about it? So how to go about it? So if I write my z as equals to x plus iota y, and if I write my fz equals to u plus iota v, what it will become? So this integral will transform into two real integrals. Yes, this is what I taught you yesterday. That is, if I'm saying my function fz dz is to be integrated over a closed curve C in region R, then this will turn into something like this, u dx, I think plus, I think minus v dy. And then there was another integration, I think u dy plus v dx. Okay, okay. And there was an iota here, sorry. Okay, so if I move on from here, just to make you, just to remind you, there's a theorem called as Green's theorem in a plane. So there's a theorem called as Green's theorem in a plane. That is in R square I'm talking. So Green theorem in R square, what does it say? It says that if I'm talking about a line integral, p dx plus q dy over curve C, I can transform it into a double integral of this sort. I hope if you remember this particular theorem. If you don't remember, please go and see your vector calculus things. This was it. And here C is a closed curve. Here C is a closed curve inside region R. Inside region R. Okay. So Green's theorem says that p dx plus q dy integral is equal to double integral over region R del q over del x minus del p upon del y dx dy. Okay. So I hope this is clear. And here p, q are some functions, are some continuous functions, are continuous functions with continuous partial derivatives. Okay, with continuous partial derivatives in region R. Okay, so P and Q are such functions which are continuous themselves and their partial derivatives are also continuous. Then you can write a line integral, you can convert a line integral of this fashion, P dx plus Q dy into a double integral. Okay, so this is your theorem. Now, coming back to our discussion. So let me write it all over again. So if I'm saying integration fz dz, so if I'm writing, sorry, if I'm writing integration fz dz, what does it mean? It means integration u dx minus v dy, as I stated before, plus integration, I think u dy plus v dx. And there would be an iota here. Sorry, again, I'm forgetting it. So v dx. Okay. Okay. So now, if I apply Green's theorem here, and if I apply Green's theorem, so if I apply Green's theorem here, what will I get? So if I apply Green's theorem here, I will get integration over R, and this will give me del v upon del x plus del u upon del y, because this will be a, and there will be a negative common out, dx dy. Okay, just see P and Q and just try to replace all these things there. And if you apply Green's theorem here, so what would you get? You will get du upon del x minus del v upon del y dx into dy. Okay, so understand, you have applied a Green's theorem here and you have applied a Green's theorem here. So we have applied a Green's theorem here and here. That is, if I am in a region R and if I'm making a closed curve C inside this region R, then this line integral over a closed curve C would give would eventually become a double integral using a Green's theorem, and this double integral will be like this. Okay, and understand my point. If my fz is analytic, that implies my the derivative of the function exists. So derivative of function exists, and also that Cauchy-Riemann conditions hold. So also understand that if I'm saying my fz is analytic, it implies what? It implies f dash z exists, and also my Cauchy-Riemann conditions hold. And further, if I say that my first order partial derivatives here, it was given what? And if the derivatives are continuous at each point within the simply connected region. So further, if I say that my derivative is continuous, okay, further if I say that my derivatives are continuous, that implies, okay, what does that imply? It implies that my Cauchy-Riemann conditions are holding. That implies what? Del u, sorry, if my function is analytic, that implies Cauchy-Riemann conditions are holding, and further the derivatives are continuous. That implies these partial derivatives are continuous. So therefore, I can use these Green's theorem. I stated this thing only, that if p dx plus q d by, there is a line integral, you can convert it into a double integral provided all these functions first order partial derivatives are continuous. So obviously this has been given in the uh, statement itself. So what you're going to get, you know that your Cauchy-Riemann condition says that del u upon del x should be equals to what? Should be equal to del v upon del y. So this gets cancelled and this becomes 0. And also it says that del v upon del x is equal to minus del u upon del x. Yes or no? So what it will become, this part will also become 0. Eventually you will end up getting fz dz c is equal to 0. Now here understand one point. There was a condition that was taken, that was the condition that was taken was what? Condition that was taken was what? Sorry. Condition that was taken was what? That if fz is analytic and its derivatives are continuous at each point within simply connected region R. So there came a mathematician called as Gorstad. Okay. So there came a mathematician called as Gorstad who relaxed these conditions. So what is, and this theorem is what we use in present form. So I would say Cauchy's Gorstad theorem, which says that if fz is analytic, if fz is analytic in R and C is a closed curve lying in this region. So we have relaxed the condition of the continuity of the derivative. Okay. So if fz is analytic in R and C is a closed curve lying in this region, then integration fz dz would become 0. Okay. So this is an important theorem. Understand, this theorem says that if your function is analytic in a region R, let's say this is your region R, and you make any closed curve inside this region R, provided this function is analytic, then any line integral over any of these closed curve would always be 0. Provided your function is analytic, the line integral over any of these curves C1, C2, C3 inside region R would give you a 0. Example, let's say first example, I would take of something like z square upon z square plus 2 integral dz, and I think I'm taking a unit circle. So if I'm taking a unit circle mod z equal to 1, what does that mean? If I'm saying I'm talking about mod z equal to 1, I'm saying that I am in a unit circle. Okay, I'm talking about a unit circle. And the function z square upon z square plus 2 dz, how to integrate it? So clearly first find what are the singularities. So it is fairly easy to see that singularities will be either, uh, plus root over 2 or minus root over 2. Okay, these two are the singularities. And you can find that in the unit circle, inside the unit circle, anywhere, at every point, your fz is analytic because the singularities lie outside the unit circle. So fz is analytic inside this region, inside the region mod z equal to 1. Yes or no? Since it is analytic, so therefore integration z square upon z square plus 2 dz would obviously give you what? Would obviously give you 0. Similarly, if you try to find integration over this unit circle with of sec hyperbolic z dz, what I can say that sec hyperbolic z is nothing but it is equal to 1 upon cos hyperbolic z, and cos hyperbolic z is e to power z plus e to power minus z divided by 2 dz. So if I'm trying to find this integral in the closed curve, which is a unit circle, then first let us find what would the singularities be. Singularities would be this way. Singularities can be written this way. Singularities will be corresponding to these points. So what would be the singularities be? Singularities would be these. Okay. The singularities are these. What are the singularities? Singularities would be, I think if you just try to place n equal to 0, you will get pi by 2, iota pi by 2, then you will get iota 3 pi by 2. And if you try to place minus 1, then you will get minus iota pi by 2, minus 3 pi by 2, so on and so forth. So you can clearly see that all these singularities do not lie inside the unit circle. They will always lie outside the unit circle. So clearly, inside this unit circle, my function secant hyperbolic x, secant hyperbolic z is an analytic function. Since this is an analytic function, I would say secant hyperbolic z dz integral over unit circle is 0. Okay, so all of these things you have to keep in mind. Okay, now a question arises. That can Cauchy Gorstedt theorem can Cauchy-Gorstedt theorem be extended to multiplicated region also? Okay. So next question that arises is whether my Cauchy-Gorstedt theorem be extended to multiplicated region as well. So answer to this problem is yes, it can be. Now there would be certain things as to how we'll be able to furnish this. So see, what I would do is I would create certain construction. These are called as slits. So what I would do, I would create a slit and I will try to make a simply connected region, multiply connected region into a simply connected region. Understand my point that my definition of Cauchy-Gorstedt theorem holds for simply connected region. Okay, it holds for a simply connected region. So let us make a multiply connected region. Let's say a doubly connected region. So I made this region C1 and C2, and I'm talking of this region. So this is clearly a multiply connected region. Precisely, this is a doubly connected region. Okay. So precisely, this is a doubly connected region. And let's say I'm saying what would be the integration of fz dz over this region R if fz is analytic in this region. मान लेते हैं कि fz is analytic in this region R. Let's say my fz is analytic in this region R, but the problem is that this region R clearly is a doubly connected region. Indeed, it is. You take any curve, so every curve, one of those curves like this way. अगर मैं ये curve लेता हूँ, if I take this curve and if I try to shrink, I will get inside the C2, which is outside the annular region. Okay, so clearly this is a doubly connected region. Okay, so how to? The first thing is try to make we'll try to make a doubly connected region into a simply connected region by introducing a slit. So what I would do, I would introduce a slit, and this slit is of the width is as small as possible. What I would do, this slit is as small as possible. Now, by introduction of this slit, so I'm talking about region R. What I have done, I've just introduced a slit. So again, I'm drawing this curve here so that it becomes clear to you. So what I would do is I would create a slit. Now, with creation of the slit, what has happened? This multiply connected region has become a simply connected region because now if you try to make any closed curve, you cannot cross the slit. So you have to be here or here, precisely here. You can be here. You can be here. You try to shrink this curve, you will be again in the region R. You try to shrink this curve, you'll again be in region R. But the point is now you cannot make a curve of this fashion because now there is a slit here. Since there is a slit, so you cannot do so. Okay, since there is a slit, so you could not make such curves which I showed in red. So now this particular region, which I'm right now telling, is almost the region R except the slit, and the slit width is as small as possible. Even if it tends to 0, this region R, just understand the region R that I'm shading in red right now. Okay, the region R red I'm like sharing right now, and this is your slit. Understand, this is your slit. This is your slit of infinitesimal small width. So what is happening is this particular region R that I'm drawing, that I'm shading right now, is nothing but it is a simply connected region. So what was initially the case? Initially, it was a doubly connected region, and because for doubly connected region we do not have a Cauchy-Gorstedt theorem. So what trick we applied? We actually converted a doubly connected region into a simply connected region, isn't it? So this is your simply connected region. Okay, because now if you make any closed curve in this red region, not blue, okay, I'm talking about red region right now. Okay, so if you make any closed curve, every closed curve in this red region, if you try to shrink that particular closed curve in the red region, it would end up being in the red only. Okay, are you getting my point? Okay, so this kind of region, this kind of slit introduction would reduces a doubly connected region into a simply connected region. Now, since it is a simply connected region, you can clearly apply what? You can clearly apply your Cauchy-Gauss theorem. So let us move counterclockwise. So I'm moving counterclockwise. Let's say this is your M, this is your, let's say, N. So this will be your N, and this will be your M. Okay, you can take M dash, N dash. So I'm moving along C1, then I'll move along C2, along MN, then I'll move along C2, I'll again move along N dash, M dash, and I'll complete the contour. So this will be now contour. So now, if I am supposed to integrate over region R, what it would be? Understand my point. Now your region R has become a simply connected region, first thing. So it has become a simply connected region. So I have extended this theorem to a multiply connected region by introducing a slit. Now, understand that over this region R, my function is analytic. I have given that already, that if my function is analytic in this region R, so this particular region R, my function is analytic. So therefore, this integration would be 0. But understand this particular region R integration can be subdivided into different integrals. So for example, if I have to write this region, if I have to write this integral, I can write integration over C1 anticlockwise fzdz, then plus integration over mn fzdz, then plus integration c1, but clockwise. Understand my point? This is clockwise. And then you will have integration along n dash m dash fzdz. Okay, yesterday I wrote a property integration a to b fzdz would be equals to what? Integration b to a negative fzdz. So this particular portion gets cancelled. So you are there are only two parts that remains here. So one part is integration fz dz anti-clock, and this is clockwise, so there will be a negative. This particular side is 0, so this will give you this. And this is a very powerful statement in complex analysis, which we know as principle of deformation of contours. Okay, so this is called as principle of deformation of contours. So understand my point. I was telling about I was initially going for making you understand as to how Cauchy-Gauss theorem can be extended to multiplicative region. And what I've got that integration over C1 is equal to integration over C2. And understand this particular region is that region is a multiplicative region, yes, and also that this particular region is a region where your function fz is analytic. That is, when I say my function is analytic, it implies I'm devoid. This particular region is devoid of any singularities. So what does this result says? That if I try to integrate over C1, if I try to integrate over C2, they are one and the same thing. That is, if I am writing C1, I can shrink this region to C2. Integration over this C1 would mean integration over this C2 if I shrink it. But the only condition is that while I shrink, the region that I'm encountering is analytic. That is, when I'm shrinking, I should not encounter any sort of singularities. In this particular region, my function was analytic, so I was not encountering any such singularity. And this is what your principle of deformation of contour says. So what does your principle of deformation of contour says? I'll write it over and do a thing that we've done already, and then we'll see all the more details tomorrow. Okay. So what does principle of deformation of contour says? So principle, and this is a very important theorem, please do understand, principle of deformation of contours. Okay, what does it say? It says the integral of an analytic function over, you can take it as fz over, I think, c1 has the same you can say magnitude of value or value over C2 into which C1 can be continuously deformed. So what it says, so value of C1 integral is equal to value of C2. And what is C2? C2 is nothing. But if you try to deform the C1 continuously, you can end up getting into C2. Okay. So the value of the integral fz over C1 is equal to value of integral over C2. But what does it mean? It means that value over C1 is equal to C2. And what is C2? C2 is a curve that can be deformed from C1. Okay. Deformed provided I would write it in this bracket, provided that in the process of deformation, 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 the curve does not encounter any singularity. So please do understand my point. What I'm trying to say, that if you have this kind of thing, let's say this is one thing and this is another thing. Let's say this is one and this is another. And let's say if my function is analytic in this region R, okay, so what you can do, you can simply deform your contour, come to this particular C2 and try to integrate here. So if your integration is difficult over C1, what you can do, you can simply deform into C2, provided you do not encounter any singularity, and try to integrate over C2. And if you try to integrate over C2 and it happens that it is easier to integrate over C2, that will fetch you the same answer as expected over integration, as expected over C1. So again, I'm reiterating and saying if you want to integrate over C1, and let's say it is very difficult or probably not easy to integrate over C1, what you can do, you can transform to C2, provided you are not encountering any singularity, try to find an integral over C2, the value will be the same as that of integration over C. So let's say take an example, and we'll see all the more details tomorrow. Okay, so the example is, let's say I'm telling you to evaluate an integral z dz. If I say that evaluate integral z dz 1 plus z square over c, where c is given by z plus 1 by 2 mod is equal to 1 by 2 traversed anticlockwise. So traverse anticlockwise means you are taking the positive sense of rotation. Okay, so I'm not going to use any other thing, but I'm going to use only the principle of deformation of contours. So I'm going to use, okay, and also this is upper half of the semicircle. So we are talking of upper half of the semicircle. So we are talking of upper half of the semicircle given by z plus half mod equals to 1 by 2, traverse in anti-clockwise direction, and integration z upon 1 plus z square dz is what is being asked. So first, let's try to make this curve. So what sort of curve would this be? I think I will make it from here. I'll make it here. Okay. Okay. So I made a curve here. What can I do? Can I do this? Why cannot do this? Okay. So let's first make what is z plus half mod equals to half. So it implies there's a circle which is upper half means semicircle. So it is a semicircle which is centered at minus 1 by 2, whose radius is again 1 by 2. So you're making a semicircle from here. Okay. So this is a semicircle which is centered at minus 1 by 2, comma 0. This is your semicircle. Okay. So again, kindly see this. This is your origin 0, comma 0. This is your point minus 1, comma 0. This is your semicircle. Okay, which is being topped. Okay, this is a semicircle, and I'm saying I'm traversing it anti-clockwise. Okay, so this is it. Okay, Now, clearly understand this particular function has singularities at plus minus iota. This particular function has singularities at plus minus iota. Yes or no? I don't think there is an issue here. Okay, so plus minus iota is, I think it will lie here somewhere, or it will lie here somewhere. So clearly, this particular curve C, closed curve C, in this particular closed curve C, which is given by Z mod of Z plus half equal to 1 by 2, which happens to be upper half of a semicircle, there is no such singularity in this region. So if I say the closed curve, this encloses no such singularity. Okay, and if I have to integrate over this closed upper half of the semicircle, is it not equal to integrating over this x-axis? Is it not equal to integrating over this x-axis? Okay, so I would say that my curve C, which is the upper half of the semicircle, can be continuously deformed into the x-axis. So my upper half of the semicircle, which is C, can be continuously deformed. It can be continuously deformed to the x-axis, because the singularities are plus minus iota. They're outside this particular region R. If I have to make R, I have made it in like this fashion. But understand my point. If I have to integrate my function, sorry for mistake. Uh, what I mentioned was upper half of the semicircle. Okay, so I was integrating over this one. Sorry. Let's come all over again to this problem. Just give me a minute. Okay, so what we were supposed to do was sorry. Okay, what we were supposed to do, we were supposed to integrate over the upper half of the semicircle. So over the upper half of the semicircle. Sorry for the mistake. So I was supposed to integrate over the upper half of the semicircle in the counterclockwise direction. So this was what was asked. So this is minus 1 by 2 comma 0. This is, I think, minus 0 comma 0. This is minus 1 comma 0. Okay. And it was asked that I have to find this integration where C is nothing but a upper half of the semicircle. So it is given that only upper half of the semicircle we considered. So this is your line. I mean, this is your arc where you are supposed to integrate z upon 1 plus z square. And I told earlier only that these are the singularities. Sorry, 0 comma 1 and 0 comma minus 1. These are the singularities. Sorry, 0 comma 1 and 0 comma minus 1 are the singularities. And I have to integrate over this curve C. This curve C. I mean, not the closed curve, sorry, but the entire curve. Sorry for my initial mistake. Just try to understand again. This is what I'm saying. I have to integrate over this closed curve C. What I can do is, instead of integrating over this closed curve C, what I can do, since my singularities are on the y-axis, they've got nothing to do with this particular region. What I can do, I can completely transform this particular C into the x-axis. Yes or no? So instead of, याद करो हमने क्या बोला था, instead of integrating over C1, you can also integrate over C2. Okay, yes or no? So instead of integrating over this upper portion, you can completely transform this particular curve to this particular point, this particular axis. Yes or no? So instead of integrating over this C, you can integrate over this particular axis, because while you are continuously deforming your curve C to the x-axis, you are not encountering any singularity. So in this particular region, there is no such singularity. So eventually, you will end up being on the x-axis only. By deforming the curve C, you will come up to x-axis, and integration over this or integration over this means one and the same thing. What is an advantage to this? Advantage to this is this particular complex integral will become a real integral, that is x plus 1 by x square. From where to where? So you are doing you are doing a counterclockwise thing. So counterclockwise means here, like it will be this way. So it will become an integration from -1 to 1. So -1 to, sorry, 0. Okay, what it will become? This will become this way. But okay, this will, if I close the curve, then it will become this way. So what I have to do is simply 1 minute. So okay, this is, if I try to deform to x-axis, what I'll get arrow this way. Sorry, I'll get an arrow this way. Okay, if I get an arrow this way, this is from my, no, sorry, it will be from 0 to -1. It will be from 0 to -1. So if I try to deform this curve onto the x-axis, what I will get? I will get a simply a line. So if I try to, again, I'm doing it. So if I try to deform this upper half of the semicircle into a line, what it will look like? It will look like this way. So this is your, I think I can write as C, and let's say some other notation, let's say C1. C1 is the line segment joining 0, 02, I think -1, 0, which is nothing but the x-axis. So x-axis, your z, you can write it as x, and simply this is, I think, 2 multiply kar do yahan pe kar do, so it will give you 1/2 ln of 1 plus x square from, I think, 0 to -1. So 1/2, I think you'll get answer as ln2 minus 1/2 ln1. ln1 is 0, so don't go about it. So 1/2 ln2. I hope it is clear to you. And if it is not clear, kindly we'll do it this problem once over again, because there was a certain issue in comprehending the question. But overall, try to understand that this is a very powerful statement. This is a very, very powerful statement, which is called as a principle of deformation of contours. Okay, so we'll take this class tomorrow. Till then, take care.